So hello everyone, welcome to Concepts in Chemistry YouTube channel. So today in this video we will discuss questions from physical photochemistry, and that will be the 18th questions in chemistry concept booster series. So let's start. So this is the questions. So the average bond energies of CH, C and C double bond O are 414,347 and 732 kilojoule per mole. The gaseous products of photodecomposition of acetone with a lambda 3000 angstrom is R. So the average bond energies of three bonds means CH single bond, CC single bond and CO double bonds are given as 414 for CH single bond, 347 for CC single bond and 732 for CO double bond, all are in kilojoule per mole. Now we have to find if we use a light of whose lambda value is 3000 angstrom, and if we use this light and to decompose acetone molecule, so if we treat this light so if we treated acetone with this light, then what will be the gaseous product? So if we use light to treat acetone, then obviously there will be decomposition of acetone. Then we have to find what will be or what are or what is the gaseous product of photodecomposition of acetone. So options are carbon monoxide and ethane, carbon monoxide and methane, carbon monoxide and hydrogen only. So the questions, the average bond energies are given, and the question is if we use light in the photo decomposition of acetone, whose lambda value is 3000 angstrom, then what will be the gaseous product after decomposition of acetone? Now let's discuss the answer so with details. So from the basic concepts in physical photochemistry, I think we all know this calculations, means how to calculate the energy of photons. So energy of each mole of photons, generally energy of, generally each mole of photon is called as Einstein. So normally energy of each photons means energy of one photons is given as h nu, that is hc by lambda. Lambda is the wavelength of that radiations or photon used. Now energy of each mole of photons means Avogadro number of photons. Energy of Avogadro number of photons is known as Einstein, and it is represented as capital E. So now capital E is Avogadro number Na into epsilon. Epsilon is the energy of one photons, means each photon. Now it's become Na is C by lambda. Na is the Avogadro number. So if we want if we want to calculate the energy value by putting the each term, that is Avogadro number, Planck constant, and that is speed of velocity of light, then in the first case, now if we express lambda means the wavelength in centimeter inverse, then by putting the value of Avogadro number and Planck constant in arc per second, because we are using lambda as centimeter inverse, and also we have to put the speed of light as centimeter per second. That's why 3 into 10 to the power 10 centimeter per second. This is CGS unit. You can say CGS unit, not SI unit. So if we put the value, then we will get 1.197 into 10 to the power 8 arc per mole. This is the energy of each mole of photons, that is called Einstein. We expressed as capital E term. Each mole of photons means Avogadro number of photons. Energy of Avogadro numbers of photons, we get the value 1.197 into 10 to the power 8 arc per mole. Now here the lambda is in centimeter inverse. If any questions, lambda is expressed in angstrom, 200 angstrom, 2000 angstrom, then first we have to transform the angstrom into centimeter. We have to first transform the angstrom unit into centimeter, then we have to put this lambda, we have to put this lambda as centimeter, then from this expression we will get the energy. In this expression, since we assumed lambda as centimeter, and by assuming lambda as centimeter we put the value. That's why if any questions there is given lambda means wavelength of light or radiations as angstrom unit, then first we have to transform that angstrom unit into centimeter, then that centimeter value we have to put here. Now if we express lambda in angstrom unit, then the expression become, just here lambda is in centimeter, we know 1 angstrom equal to 10 to the power minus 8 centimeter. Just in this place we have to put 10 to the minus 8 term, then this lambda become angstrom unit. So if there is any questions and in the questions the wavelength is mentioned as angstrom unit, then in this box, the expression within the box, the expressions 1.197, this 10 to the minus 8 goes up, then it's become 10 to the power 16 arc per mole, and here the lambda is in angstrom unit. So in the questions, if lambda wavelength of radiation or light is given as angstrom unit, then in these expressions there is no need to transform the lambda value into centimeter. We just we can put the lambda as angstrom unit in these expressions, but in the previous expressions, in these expressions we cannot put the lambda value as angstrom unit. So 2000 angstrom, if it is given as 2000 angstrom, we cannot put here 2000 because here lambda is in centimeter unit. We have to first transform the lambda into centimeter, then we can put the centimeter value. But in these expressions, if lambda is mentioned and as 2000 angstrom, then we can put, we should put here, we should have to put the angstrom value, not the centimeter value. In these expressions, if there is if any question there is mentioned lambda as angstrom unit, then in this expression 1.197 into 10 to the power 16 by lambda, in this lambda in these expressions we should have to put lambda as angstrom unit, whether it is 2000 or 1000 or 4000 angstrom, we have to put just the angstrom value, no need to transform the value into centimeter. So this is in arc per mole. Now if we want this expression in joule per mole, just we have to divide this whole expression by 10 to the power 7, then it will become 1.197 into 10 to the power 9 joule per mole. In this expression also lambda is in angstrom unit. If there is any questions, lambda is mentioned as angstrom, then we have to put just the angstrom value here. This is joule in joule per mole, 1.197 into 10 to the power 9 joule per mole. If we want this expression in calorie per mole term, then we have to divide this whole term by this joule term by 4.2, because we know that 1 calorie is equal to 4.2 joule. So it's become 2.864 into 10 to the power 8 by lambda. Here also lambda is in angstrom unit. So in these equations, arc per mole energy is expressed at arc per mole 1.197 10 to the power 16 upon lambda in angstrom unit, 1.197 into 10 to the power 9 upon lambda joule per mole, 2.864 into 10 to the power 8 upon lambda in angstrom unit calorie per mole. So I hope you all know this basic calculations from photochemistry. To solve any numerical questions from physical photochemistry, we should know these calculations. So now move to the questions. So this is the basic calculations to calculate the how to calculate the energy of photons, energy of each mole of photons. So now, so in the given questions, see the questions, they used a light whose wavelength value is 3000 angstrom. So in the questions angstrom is given, so and the energies and the energies are expressed as kilojoule per mole. So we have to use the expressions joule, the energy which is expressed as joule per mole. So first we have to calculate the energy of the corresponding wavelength. So they used the wavelength whose wavelength is 3000 angstrom. So now we have to calculate the corresponding energy, means the Einstein or capital E value of the corresponding wavelength. So we use the joule per mole expression. These expressions 1.197 into 10 to the power 9 joule per mole upon lambda. Lambda is in angstrom unit. So in the questions lambda is given 3000 angstrom. So we just want to calculate the energy of corresponding energy of the wavelength used. Then we have to put this expression 1.197 into 10 to the power 9 upon 3000 angstrom. See, in these expressions here lambda is in angstrom unit. So that's why we just put the angstrom value directly in this expression. So from these expressions, if we put the lambda value here, then the energy of, so the energy we will get, that is the energy of 1 mole of photons, that is called Einstein or capital E. Then E will become 399 kilojoule per mole. 399 kilojoule per mole. If we put the lambda value in these expressions, then the corresponding energy of the wavelength used become 3.399 kilojoule per mole. Now see, in the given questions, the average bond energy are given as Ci single bond 414 kilojoule per mole, Cc single bond 347 kilojoule per mole, C double bond O 732 kilojoule per mole. But we are using a light. Now we don't have to consider the wavelength. Now we are considering the energy. We calculate the corresponding energy of the wavelength used. So we are using a light whose energy is 399 kilojoule per mole. Now in the acetone molecule there are CH bond, CC bond, C double bond, O bond. So the bond energies of CH is 4 on 4, that is greater than the energy we are using for decomposition of acetone molecule. CC bond 347, which is less than 399. C double bond O 732, which is more than 399. Now we are using a light whose energy is less than CH bond and C double bond O. So this energy corresponding light, so the light corresponding this energy cannot break this bond, CH bond and C double bond O bond, since it is less than this CH average bond energy and C double bond O average bond energy. Since this energy we are using, the energy corresponding light we are using is greater than the CC single bond average bond energy, then it will break the CC single bond. So we all know in the law of photochemistry, that is there are two laws. So now we all know the two basic laws from photochemistry, that is one is Gotha's-Dropper's law and the another is Stark-Einstein law. So from the first law, that is Gotha's-Dropper's law. So it says that in a photochemical reaction, so only that light which is absorbed by a substance can cause photochemical changes. So the light which is absorbed by the substance can cause the photochemical changes. Means, so here the energy of the light we are using 399 kilojoule per mole, but the Ca is average bond energy is Cc 347. So this is more than the average bond energy of Cc single bond. So by this means we cannot say that this energy will break this Cc bond, because this is more than that the Cc single average bond energy. So it is greater than, okay, it's okay, but to break this Cc bond has to absorb this light. We are using a greater energy containing light, so that we are using a light whose energy is greater than any bond. It does not means that it will decompose, it will break that bond, but we have to use either same amount of energy or greater amount of energy to break a bond whose bond energy then the, so we have to use a light whose energy is greater or same as the average bond energy of the bond. But to break, to photochemical decompositions, it is the primary criteria is the bond, the Cc or any bond has to absorb the light. If there is no absorption, we are using a greater energy containing lights, greater energy corresponding light we are using to break a bond. But if the bond will not absorb the light, then there is no bond breaking. We are using a greater energy than that average bond energy of the bond. Still, if the bond will not absorb the light, then there is no photochemical decomposition or there is no photochemical reaction. So the bond has to absorb that light. So this is a some basic principle in photochemistry, physical photochemistry. So to Cc, to bond Cc, to break Cc bond, so the Cc bond has to absorb this light. So so obviously by observing some theoretical data, so we are using a particular light which should absorb, which should have to absorb this Cc bond. So that's why we are using a particular light. So in this case, so there is no questions about this CH and C-double-bond O bond, because the average bond energy are greater than this energy we are using. We are using the light, corresponding energy is less than that of the CH and C-double-bond O bond. So now only by this light only Cc bond can break, only Cc bond, Cc single bond can break. So now what are the possible decomposition? So this is the acetone molecule. There are Ci single bond, C-double-bond O and Cc single bond. So by using this light, we saw that the corresponding energy we calculated of this light. So by this light only this Cc bond can break. The CH bond and C-double-bond O bond cannot break by this light. So only Cc single bond can break. So if we use this light, the Cc single bond can break and it will form, this bond will break, form CH3 radical, this bond will break to form another CH3 radical. So two CH3 radical and this become CO, carbon monoxide molecule. So after photodecomposition of acetone with this light produce carbon monoxide and two methyl radical. Now these two methyl radical may combine to form ethane and this carbon monoxide as a carbon monoxide. So we know the carbon monoxide as a gas. So after photodecomposition of acetone using a light whose lambda value is 3000 angstrom, the gaseous product are carbon monoxide and ethane. So the correct options of these questions is option A, carbon monoxide and ethane. See, if we used a light, by this light, if there is breaking of CH bond also possible, if that light breaks the CH single bond, then there will form hydrogen radical, means lot of hydrogen radical. Then we can say hydrogen radical combine to form H2. So we can say hydrogen gas, the gaseous product will be hydrogen if they if a light break the CH bond. If a light break CH bond as well as CC bond, this CC bond, then we can say methyl radical will form by breaking this CC bond, and by breaking the CH bond, hydrogen radical will form. Then this methyl radical and hydrogen radical may combine to form methane gas. In that case, methane gas also evolve. So in this case, only two methyl radical form, they combine as to form ethane and carbon monoxide. So the carbon monoxide and ethane gas in this case evolved after photodecompositions of acetone. So I hope these questions will help you a lot to solve different type of questions from physical photochemistry, and I hope you understood what I am trying to say by this by solving these questions. So uh, so thank you for watching. Stay safe, stay healthy.